Alright, so what we're going to solve here is a power factor correction problem. And anytime that we're going to do power factor correction, it is usually best practice to go ahead and find the total power triangle. So I've set up this problem where that's what we're going to find first, is find the total power triangle. And really, there's two ways to go about it. We can look at each individual component and the power going through it. But whenever we're given the problem where we have the ohms of each of these, note for the inductor, I've already put the J component on it, but anytime that we're given the ohms, it's best to find the Z total first. And the reason why that is because we're going to use Ohm's law that says V equals IZ, and we're going to rearrange to find I total, and then we're going to use that I total to then find complex power. And really, I would say finding total complex power, being the vector, the source complex power, if you can do that by adding the P's and the Q's that you could be given in the components, or if you aren't given the P's and the Q's, it's probably best to just find it with the Z. Then we'll use S equals VI complex conjugate. And we'll solve for the total complex power. So the first one is Z total. We can see right there 20 and 30J are in series, 20 plus J30, and that is in parallel with 60. They share the same two nodes on the outside. We put those together, we get 25.32 angle 35.73 ohms. That's our Z total, so now we can solve for I using V over Z. The V is given in the problem statement, 120 angle 0, Z 25.32 angle 35.73. That gives us 4.74 amps angle negative 35.73. That's supposed to be a 7. All right. So now we have I total. We can plug each of these in. V, it's the same V that was given in the problem statement. The I, 4.74. And now the complex conjugate makes this a positive 35.73. Right there to there, complex conjugate. And that is just reflected on the real axis. So we just change this angle. The magnitude stays the same, the angle is the opposite. We put both of those together, we get 568.72 angle 35.73. When we have this in the polar form, which is what this is, what we already have is S, and on the angle, we have the theta that's going to go inside the triangle. The S here being the magnitude, which is apparent power. Apparent power. And simply going from polar to rectangular, without even solving for anything, we just do the polar to rectangular in the calculator, we get 461.4 plus J 332.5. This is still the complex power, but now this portion is the P total, the real power total, and this is the Q total. So simply solving from polar to rectangular gives us all four parts of our power triangle. Now this is an inductive power triangle because this is a positive theta angle. Note this angle is the same as the Z. And that's always true. Theta of the triangle is equal to the theta of the Z. This is inductive, 332, 461. So here's the triangle right there. This is 332.5 VAR. This is 461.4 watts. This hypotenuse is 568.72 VA. I could note this is inductive, but the triangle already says that because it's pointing up, and this angle is 35.73 degrees. So if you were asked to find a total power triangle, that's how you would solve for it. The last step, would be the power factor, which is P over apparent power. And if I just take those ratios, 461 divided by 568, I get 0.81. So this is the total power triangle, and what we see is that the power factor is not at unity. So the next part of the problem is we're going to bring the power factor to unity. That means that the power factor will be 1. Another way of saying it is that P will equal S. Another way of saying it is that the sum of the Q's will equal 0. And so if the sum of the Q's is going to equal 0, then what we need is we need a Q of the capacitor to be 332.5 VAR. It'd be negative because we're going to cancel out this positive 332. The quickest way, if I'm going to solve, I'm going to correct from the source, is to use V squared over X. There's other formulas that would give you the Q, or the X needed rather, because what we're going to do is we're going to rearrange the equation to solve for XC, V squared over QC. But this is the best one because we're going to correct it from the source, and we already know the source voltage. It's just its magnitude, so we don't need the angle, 120 squared over 332.5. If you want to be technical about it, we need a negative and a negative, but those cancel out. So it doesn't really matter. As long as your X is positive, the negatives will cancel out. And what we get here is 43.31 ohms. The final answer is not asked for in ohms, though. We've given a reactance, but we need the capacitance. Well, we have the equation for the capacitance, 1 over 2 pi FC at the top of your formula sheet. We can rearrange for the C being capacitance, 1 over 2 pi F XC, and we're going to solve for the C, 1 over 2 pi 60, XC being 43.31, and the C comes out to 61.246 microfarads. And if I plug that capacitor in parallel, plug in parallel to the source, and that's so that we have the source power factor being corrected. So as long as it's between the nodes, you could put it here, you could put it here, you could draw it on the outside. As long as it's between the same two nodes from the source, then you will correct the source power factor correction. The last step that we're asked to solve for is to find the source current before and after. Well, the I before, we already solved for. 4.74, angle negative 35.78. The I after, right, I after would be the V over the Z after. And what is the Z after? I'll solve for it right here. Z after, we've plugged in the 43.31 in parallel with the 60, 43.31 negative J, excuse me, because it's a capacitor, within the 60 and then the 20 plus J 30. Together that gives us 31.2 angle 0 ohms. And that makes sense that after power factor correction, it is just resistive. This 0 angle means it's just resistive. These two canceled out, the negative J 31.31 and the J component over there. When we plugged it all in, that's what was canceled. 120 angle 0 over 31.2 angle 0. And the I after is 3.85 angle 0. This is less than this, which is the goal of power factor correction, is to minimize my I for several reasons. One of the big ones being that we want to minimize the I squared R losses in the line. And if you look back to the lecture, we have other reasons, smaller source generator. And in real life, we would never bring it fully to 1. We'd bring it somewhere around 0.95. But for the purposes of this class, bring your power factor to unity by 1, and then you will minimize the current.